the fraction one again, and then 1 second.
In 3, 2?
Yeah, 16, 17, and 20. So, you did both of these yesterday, or similar ones.
Like 16 and 17 I did, yeah. Didn't do one like 20. Let's go ahead and do that one.
Okay.
I think for 16 and 17, I might refer you to video from yesterday.
Okay.
If that's not good enough, let me know.
Okay. Will do. Thank you.
Welcome. Go ahead and share my screen here. Okay, I copied over question 20 from my homework. So we'll take a look and see what we've got here. Yours will be similar, probably different questions or different numbers. So we've got a box made by cutting this cardboard, or tin, I guess it is. It's 20 centimeters by 60 meters. They're cutting these corners out here, like those, and then they fold up this edge, so this becomes a folded edge there, and a folded edge on the side, and those fold up and make this box. And so they tell us the area of the base down here is 624 square centimeters. Okay, so that's the area inside the dashed line. And as we know, area of a rectangle is length times width. So we need to figure out the length and the width of that rectangle. We don't know the size of those squares they're cutting out. And when we don't know something like that, that in algebra is the time we start throwing a variable at it. So I might call that x. And if it's a square, then this side has to be x. And if they're all the same sides, then every single one of these has an x. So this distance right here, that's the length of the base, would be 60 minus x, which I could say is 60 minus 2x. That's that length inside there. We would do the same thing on the side. That would be the full 20 minus an x for the upper rectangle and then an x for the lower rectangle. So this would be 20 minus 2x inside there. So now I've got a length, I've got a width, I've got the area. I should be able to plug these in. So area equals length times width. I know that the area is 624. We just decided that the length is 60 minus 2x, and that the width is 20 minus 2x. And so I should be able to work this out just fine. Let's do a little foiling. 60 times 20 is 1200. Then we've got outside 60 times negative 2x minus 120x. And we've got inside negative 2x times 20 minus 40x. And we'll do last, negative 2x times negative 2x is a positive 4x squared. And that still equals 624. So let's combine some like terms and get everything on the same side. So now I've got 0 on the left here, 1200 minus 624 looks like it's probably 576. Double check that just in case. Combine some like terms, minus 160x, and then plus 4x squared. See, it looks like 4 will go into everything. So I'm going to divide everything by 4. 0 divided by 4 is 0. 576 divided by 4 looks like 144 minus 40x plus x squared. Okay. And recall that I'm solving for x, right? What is the length of the sides of the square? So I'm solving for x. Let me rearrange this so it's in the format I'm used to with the x squared first. And so now I've got a, b, and c. I may be able to factor this directly. I don't know that I can, but I may be able to. I may be able to complete the square, but I know I can use the quadratic formula. That one I know. So I'm just going to go ahead and do that rather than try to find factors of 144. It's probably not that hard to do that, but opposite of b plus or minus the square root of b squared minus 4ac all over 2a. It's my quadratic formula. So the opposite of negative 40 plus or minus the square root of negative 40 quantity squared minus 4 times 1 times 144 all over 2 times 1. So that's a positive 40. Let's see. So 40 squared would be 1600. And subtract from that 4 times 144, which we know is 576. We did that earlier. So that gives us 1024 inside here. All over 2. The square root of 1024 is 32. So we've got 40 plus or minus 32 over 2. Well, that gives us the two different options. We've got plus or minus. If it's plus, we've got 72 over 2, which is 36. If it's minus, 40 minus 32 is 8 over 2. That's 4. So looking at our box here, if I tried to cut a square that's 36 centimeters from this side, 36 centimeters, 36 centimeters, it won't fit within the 20. So very clearly, that is not the solution to our initial problem. It is a solution to the algebra, but it's not a solution to our problem. The solution we want is 4. So x equals 4 centimeters would be what we're cutting off. Now we can check that. This is 4, and that's 4. We've cut 8 off. This becomes 12. If we cut 8 off of 60, I'll do it down here, this becomes 52, and 12 times 52 is our 624. I just checked it, and that is true. So we were able to double check that that works. So that's how we would solve that. Kind of thinking about, well, what would this look like? What are the sides of the base of the box once I cut it? How can I represent that algebraically? And then we end up with a quadratic. Quadratic formula works really well for that. So hopefully that helps. Let's see, that was question 20, right? Yeah.
Yeah. Could you reduce it before you actually did the plus or minus?
I could. If I reduced both of those, I would have 20 plus 16 is the 36, and 20 minus 16 is the 4.
Okay.
That works. I just have to make sure that I divide both of those by. But yeah, we can do that. It basically becomes 40 halves plus or minus 32 halves, which is 20 plus or minus 16. So definitely an option. I would be careful with that. I've seen a lot of students do something where they've got like 40 plus or minus 2 root 3 over 2, and they say, oh, that's 20, so it's 20 plus or minus 2 root 3, and they forget to cancel over here too. So be real careful when you are canceling in the middle that you remember to cancel everywhere it applies. But if you do that, you're fine. All right. Any other questions? That's more people, so I'm going ahead to mark people here. I've got Christopher and EJ. Let's get Eric and Honoria and Igor and Phil. All right. Okay. If I don't see any other questions, so let's go ahead and look at 3.3. I'm hoping we can get through 3.4 as well today, because this week we're covering through 3.5 as well as 4.1. We may not be able to get through all of that in this session, in the 142 session, but we will at least get through a bunch of it. So one of the things we want to talk about specifically for 3.3 is graphing a quadratic. So if we've got a quadratic like this, y equals x squared, that was one of our parent functions when we were talking about transformations. And if we plug some values in, we plug in 0 for x, we get 0. Plug in 1, we get 1. Plug in 2, we get 4. Plug in 3, you get 9. Plug in -1, you get 1. -2 gives us 4. -3 gives us 9. This is being one of our parent functions. It's one we know, and we'll use it a lot. It shows up again in chapter 10. So that's y equals x squared. In the section where we talked about transformations, we talked about adding inside and outside of the function. So we might come up with, say, something inside. So before it gets squared, we talked about vertical stretch or shrink. Maybe we put a 3 out here. We talked about a vertical translation, maybe a +2. And so thinking about that, our vertical translation is up 2. So from any point, you can go up 2. Our horizontal translation was 2, so we could move over 2. And that would be the point that was originally this deflection point down here. I just moved it up 2 and over 2, so now we're there. If we plug in for this 3, so we plug in the next value of 3. 3 minus 2 is 1. Square that is 1, times 3 is 3, plus 2 is 5. So at 3, we're now at 5. I think you'll find if we plug in a 1, we'll also get a 5. So the vertical stretch is in effect, and this thing becomes real vertical. It's skinnier because of that 3 out front. So that fits with our transformation discussion. But notice, something we need to really pay attention to here is that point of deflection where it changes, or inflection, I should say. So it's changing direction there. That's called our vertex. And notice that vertex is those 2 points, 2, 2. So it turns out that our general function for these quadratics looks like that. And the vertex is at HK. That's the ordered pair that describes exactly where that point of inflection is. And for these parabolas, that is the minimum. The y value of that, the k, is the minimum. And sometimes they'll say at x equals h. Sometimes they'll ask for the ordered pair, so watch that blue text. But that is the minimum value for all of these. Now, sometimes we get those parabolas that open down like that. So again, this is my vertex, my HK. We would just have a negative out in front because we're reflected about the x-axis. Well, now that becomes our maximum. So the maximum is also k, but only for those parabolas that open down, again, at x equals h. So the k is the maximum or minimum, depending on the shape of the parabola, and that is basically the sine of a. So that gives us that shape. There's another concept we want to hit on here, and that would be looking at the blue parabola. We've got this line going down through the middle. In this case, it's the y-axis, and the parabola is symmetric about that. If we look at the red parabola, it's symmetric about that line. So that is a line about which this given parabola is symmetric, and they call that the axis of symmetry. That is the line about which your parabola is symmetric, and that will always be x equals h. For all of these parabolas that open up or down, it will be x equals h. And so you will be asked, given a function, what is the vertex? What is the minimum or maximum? What is the axis of symmetry? And so you'll need to find these. Now, one of the things I want to point out here is that we've got this binomial squared. And I mentioned this earlier this week, that one of the tools we have available to us that will give us a binomial squared is completing the square. So we will want to complete the square for this work. Let me go ahead and add another layer. We'll pull up a problem and find all of these data points or data items. Say we've got f of x equals x squared plus 10x plus 23. Now I know this is a parabola because it's a quadratic equation. I know it's quadratic because the largest exponent is a 2. Being a quadratic, it will make a parabola if I graph this. So let me go ahead and complete the square on this. Now I'm going to do this just a little differently from what we did before because I don't have a number over here on the left-hand side. I've just got this f of x notation. So what I'm going to do is leave a little space and move my 23 over here, and I'm going to complete the square inside the parentheses on the same side of the exponent, or same side of the equation. So I'll bring down this middle term, divide it by 2, and then I square that, and add it in. Now, if I add 25 on the right, I can subtract 25 on the right, and I've done nothing, which is kind of silly, I know, but now we have it ordered in a way that we have a perfect square trinomial. And that perfect square trinomial is going to factor immediately into the variable, and then that final term, the square root of the third term, or the middle term divided by 2, those are the same thing, squared. And then I've got plus 23 minus 25, so minus 2. And now this is in that form that I needed, where I've got f of x equals a times x minus h quantity squared plus k. It's in that form. So let's see what I know. I know that a equals 1. There's nothing in there, so I know that's a 1. I know that h equals negative 5, because what is subtracted from x here? A negative 5. X minus negative 5, we write as x plus 5. K is negative 2. So now I have the vertex. That's hk, so negative 5, negative 2. Because it's positive, this thing's going to open up, so I don't have a maximum, but I do have a minimum. What did I write? Minimum? The minimum will be the k value, and that is at x equals the h value. My axis of symmetry is at x equals negative 5. So if I wanted to graph this, we could start at the vertex, negative 5, negative 2, be right there. I know it opens up. The axis of symmetry is at x equals negative 5. That's this vertical line right there, goes right through the vertex, and it better. And now I can either pick x values that are next to the vertex, say negative 4. If I plug that in, and I'm plugging them into this formula here, so negative 4 plus 5, let's do that. Let's do an f of negative 4. Squared minus 2. Negative 4 plus 5 is 1. 1 squared is 1, minus 2 is negative 1. So that's going to be here. We could do an f of negative 6. And due to symmetry, it better be the same y value, right? So negative 6 plus 5 is negative 1. Negative 1 times negative 1 is a positive 1, minus 2, negative 1. So we're there. And you'll find that it will be shaped just like the parent function was rising up. So that would be my parabola. And I read hk right off of the formula. And we should note, I said h is negative 5, but this said x plus 5. And that is simply because my original formula has x minus h in it. So we need to see what is subtracted from x. And the value subtracted from x is negative 5. All right, have you got any questions on that? All right. Now I need to jump to another idea, and that is specifically dealing with that maximum or minimum. So if I have a parabola that does something like this. Say I launch something from the 3 here and it goes up and changes direction, drops back down to Earth. I've got some maximum right here. That max is going to occur at the vertex. And so I need to find that vertex. I could do completing the square. It's going to work fine. Sometimes I don't want to put in that much work. I don't know if I've told you yet, but I'm pretty lazy. So if I can take my x values here, those are the zeros. If I can find the point that is exactly halfway between them, that would be the x value of my vertex, right? Because that's right on the axis of symmetry. So if I used my midpoint formula with those two, and recall that these are negative b minus the square root of b squared minus 4ac all over 2a, and negative b plus the square root of b squared minus 4ac all over 2a. Those are those two zeros. I use the midpoint formula, so I'm going to add those two together and divide by 2. You will see that negative, the determinant, plus positive determinant will cancel. So I end up with negative b over 2a plus negative b over 2a divided by 2. You will find that the x value of the vertex is negative b over 2a. The y value at the vertex will be the function evaluated at that x value. I'm not going to derive the whole thing. It's in your book. But that's our vertex formula. If all you need is the vertex, all you need is the maximum or the minimum, this is a great way to do it. Because then you don't have to find the zeros. You don't have to find the transformations or anything. We just plug it right in and get our vertex. Let me show you what I mean. So if I've got f of x equals negative 2x squared plus 10x minus 23 halves, and I need the vertex, I can complete the square on this. I'd have to factor out the negative 2, leave some space. I mean, I've got this fraction, negative 5 divided by 2 squared. I'd be adding 25 over 4, but really that's times negative 2. So you can see this is getting ugly pretty darn fast. So I don't want to do that because all I need is the vertex. So to get the vertex, A is negative 2, B is 10, C is negative 23 halves, but I don't need that for my formula here. I just need negative B over 2A. And then the function evaluated at that. I'm just going to go ahead and put x for now because I'm simplifying this. 2 times negative 2, well, you know what, the negatives are going to cancel each other. 2 goes into 2 once, goes into 10 5 times. So I do end up with that 5 halves. And then I need my function evaluated at 5 halves to get the y value. So 5 halves squared is 25 fourths. But multiply that by 2, and it's going to basically that's going to be a 1, that's going to become a 2. So we end up with negative 25 halves. Same kind of thing is going to happen here, but maybe I should leave it in halves since everything else is in halves. And just plus 50 halves minus 23 halves. Negative 25 minus 23 is a negative 48 plus 50 is 2 halves, and that's 1. So all of this is really just 1. There's my vertex. I didn't have to go through the complete the square. I just did negative b over 2a. And that gave me the x component, and then I plugged that into the function to get the y component. And that's great mathematically, algebraically. Looks good on paper, but let's actually use it in a real-world application, like this one. A landscaper has enough stone to enclose a rectangular koi pond. Some things I need to pay attention to is it's a rectangle. That's going to allow me to calculate area next to an existing garden. So they've got a garden here. Assume that I can draw a straight line. Rectangular pond next to it. I've got 24 feet of wall. So I've got a width, a length, and a width. And those three together equals my 24 feet. If the garden wall forms one side of the rectangle, what is the maximum area that we can enclose? And what are the dimensions? So let's figure out a good way to denote this. If I leave that W, let's see, let me solve for L here. So I combine my like terms. I've got now L plus 2W equals 24. Subtract 2W from both sides, and L equals 24 minus 2W. So I'm going to replace this L with 24 minus 2W. Now I only have one variable. Makes it much easier to do the work. The area of a rectangle, we already said, is length times width. So that equals 24 minus 2W times the width, which is W. So distribute this W through, and I get 24W minus 2W squared. That's the area. Let me rearrange that so it's in a form we're used to seeing with the squared term first. So the area of this pond is denoted by that formula right there, which is a quadratic, which means if I graph that formula, it's a parabola. And this negative out in front says it's a parabola that opens down. So it's going to look something like that. I want to maximize area, right? What is the maximum area? Well, that's my vertex. That's the maximum, just like we talked about. So let's go ahead and find that. The x component is negative b over 2a. So negative 24 over 2 times negative 2, that's negative 24 over negative 4, which is a positive 6. Now, what is it we're talking about when we're comparing this? This, I wrote x here. It's actually w. It's our independent variable. So this would be the width. The actual area is what you get when you plug that width in to the formula. So negative 2 times 6 squared plus 24 times 6 6 squared is 36 times negative 2 is a negative 72. 6 times 24 is 144. And negative 72 plus 144 is a positive 72. And that would be square feet. So my answers, W equals 6 feet. 24 minus twice W is 12 feet. 24 minus 2 times 6. And 6 times 12 is 72 square feet. So we were able to find the dimensions of a rectangle whose, it's not really perimeter, but the lengths of 3 sides, lengths here, here, and here, I'll add up to 24. The maximum area I can get is 72 square feet, if it has to be a rectangle. If I were able to do a semicircle, it would give me more area, but we were limited to a rectangle. So that's a time we can use this vertex formula, because we were asked to maximize area. And it'll do that. The first variable in the vertex is the independent variable in the function. The second one is that function equals y value, say. Let's do another one like this. A little different, but somewhat similar, in that we are asked to determine the time at which the rocket reaches maximum height. And what is the maximum height? So again, it's a maximum. We have a quadratic equation because we've got a squared term, and it's negative, so it opens down. That tells me I've got a parabola like this. The maximum occurs again at the vertex. All right. Now, what they say, a model rocket is launched with an initial velocity of 100 feet per second from the top of a hill that is 20 feet high. There's the 20, there's the 100. They've already taken care of that for us. Its height in feet, t seconds after it's launched, is this function. So s is height, t is time. All right, so they want us to find the time, maximum height. So once again, we've got our parabola. We've got a t-axis. We've got an s-axis, height versus time. The time at which it's at its maximum, that's like the h of our vertex. The maximum height itself is the k. So we're good. Let's go ahead and solve this thing. So the time is the negative b over 2a. And I went ahead and used time since that's the variable in our function. Negative b is the 100, over 2 times the a, which is negative 16. So we've got negative 100 divided by negative 32. If you get a positive, you might want to double check your work because our time machines haven't worked out yet. So you shouldn't have a negative time. 3.125 seconds is the time it takes to get to the maximum. What is the maximum? Well, let's go ahead and plug that in. So we want S of 3.125 is negative 16 times 3.125 squared. Plus 100 times 3.125 plus 20. So 3.125 times negative 16 is a negative 156.25. plus 312.5. That's 100 times 3.125. You can just move the decimal twice. Plus 20. Gives me 176.25. That would be feet. So we've got the time and we've got the height, all from the vertex formula. You can see that saves us time over trying to complete the square and getting this into that other vertex formula. But all this gives you is the vertex. It won't give us the zeros down here where it hits the ground. It won't tell us how long it takes until it hits the ground. And so finding some of those other things, like plugging this into the quadratic formula, will give you that distance. Because thinking about this, what is the height when it hits the ground? 0. And so then we can just plug that into the quadratic and figure out what that time is. We know the height, but we can get the time there. Those are things that we can get with some of those other tools. The vertex formula, that negative b over 2a, and then the function evaluated at that, will give us the maximum, and in this case, the time it took to get to that maximum. Do you have any questions on that? Okay. Well, that is the gist of 3.3. And again, it feels like we go so fast in here, but there's just a lot to cover. I'm going to jump into 3.4 real quick to at least get us started on that. With 3.4, we are now kind of leaving the quadratics for a minute. We're going to solve rational and radical equations. A rational expression is basically another way to describe a fraction that has a variable in it. And so if I have something like x minus 8 over 3, that's a rational expression. If I somehow make an equation out of that, now I've got a rational equation. One of the easiest ways to solve one of these is to clear the fraction. And so if we multiply everything by a common denominator, we can clear that fraction. I see a denominator of 3 and one of 2. I know that both of those numbers will go into a whole host of numbers, but 6 is the smallest one I can think of. So now, if I distribute that 6 through, I can simplify this a bit. So 6 divided by 3 is 2, so I end up with 2 times the numerator. And 6 divided by 2 is 3, so here in the middle one I've got 3 times its numerator, and 0 times 6 is 0. Once again, do a little distribution. 2 times x is 2x. 2 times negative 8 is negative 16. 3 times x is 3x. 3 times negative 3 is negative 9. Combine like terms gives me 5x minus 25 is 0. Add 25 to both sides. I've got 5x equals 25. Divide by 5. And I end up with x equals 5. Now this is a section 3.4, where you definitely want to check your answers, especially if there's a variable in the denominator, Go ahead and check this real quick. 5 minus 8 over 3 plus 5 minus 3 over 2 equals 0. And the reason we're going to want to check is because we have some domain restrictions on some of these. And if you get an algebraic answer that is outside of the domain, it is not a part of your solution. And it looks like this one checks okay, so I'm pretty good with that answer. Let's do another one where we do have a variable in the denominator. And you will see the importance of checking our answers. Let me hide that and do a different one. X squared over x minus 3 equals 9 over x minus 3. So I can multiply by that least common denominator, which is x minus 3. Well, let's go ahead and we want to distribute that through. When I do, we'll end up with x squared equals 9. Because those denominators will cancel. Take the square root of both sides because we need to solve for x, and x equals plus or minus 3. So we have our two answers, which we might expect because we've got an x squared up there. Now let's go ahead and check those answers. So if I use my plus 3, I've got 3 squared over 3 minus 3 equals 9 over 3 minus 3. So 9 over 0 equals 9 over 0, but I can't divide by 0. So plus 3 is not a solution. It didn't check out very well. Negative 3 squared over negative 3 minus 3 equals 9 over negative 3 minus 3. So now I've got 9 over negative 6 equals 9 over negative 6. That works. So negative 3 is the solution to this particular problem. Now we could see just by looking at our initial problem that down here in the denominator, x cannot equal positive 3. We knew that because if we put positive 3 in, we would end up with a 0 down there. And so even though we got a solution down here algebraically that included positive 3, we knew it was. And so we could have discarded that if we had looked at the domain first. We didn't, and I didn't on purpose so that we could check and see that one of those actually doesn't work. That's something you really need to watch out for in this section, is that your solutions are actually viable given the domain restrictions. Let's look at another type of problem. This is a radical equation. When I was a kid, radical meant really cool. I suppose it's really cool. But okay, we've got a radical here, and to clear the radical, what we'll do is we'll square both sides. Because if you square a radical, you end up with just the radical. I should say it, if you square a square root, you end up with the radicand, the value inside the square root. So this would just give us 3x plus 1. Squaring 4 gives us 16. Subtracting 1 from both sides, 3x equals 15. Divide by 3, x equals 5. Let's check that. Square root of 3 times 5. Plus 1. Does that equal 4? So the square root of 15 plus 1 is 16. Square root of 16. So that works out okay. So 5 is a viable solution. Again, we've got some domain restrictions. We can't have a radicand under a square root that is negative. So we could have said, well, my domain restriction is 3x plus 1 has to be greater than or equal to 0. Subtract 1, we get 3x is greater than or equal to negative 1. Divide by 3, x has to be greater than or equal to negative 1/3. That was our domain restriction. We came up with an x that fit within that domain, so we could be pretty comfortable with that. Doesn't always algebraically work out to give you something in the domain, in which case there may not be a solution. Or like we saw up above, you might not be allowed to keep one of your algebraic solutions. So we have to watch for that. And we're out of time. We can add to this a bit more tomorrow if we need to. So I would kind of like to just jump into 3.5 and 4.1 a little bit, but get started on the homework tonight so that if you have questions tomorrow, we can talk about that. But before we leave, do you have any questions now? That felt way too fast. I wish we had that hour of 1:43 to introduce the material that we could then just talk about a bit more in here.
I think it'd probably be pretty nice.
It would be. I wish we were face to face again. I like this. I like working in Photoshop, but I miss the face to face and I miss the extra time we had when we could do both classes. All right, well, let's call it a day. If you have questions, feel free to email me or bring them up tomorrow and we'll go over some more. We may not get through all the way through 4.1 tomorrow, but the book does a really good job of describing what's in there. All right, have a good day, and I'll see you tomorrow.
Thank you.
Thank you, you too.
Welcome.